Hi, we're uploading this video because in the lecture Explainability from our course, somehow the recording of the audio didn't work for the first 30 minutes or so. So this wants to fix that. And yeah, so exactly as I said, we're in the lecture about explainability. In the first two lectures, we've looked at, well, first of all, large language models. In the first one, which ones are out there, the main players, and so on, and what's like the core technology that most of them are based on, and what are the different ideas that led to their development. And in the second one, we've looked at fine-tuning techniques. So that is not how large language models work, but effectively how to use them when you don't have available too much data in settings where your data sets are not too big, or perhaps you want to apply a large language model to a specific use case quickly with only providing perhaps a few examples. All right, so now it's about explainability. So as we saw in the last lectures, these models are getting better and better. We're now able to do things that 2 years ago I would say were even unthinkable. But of course this has come at the cost that models have become way more complex, and the original, like the very old ones, like linear classifiers and so on, they were very easy to understand just by looking at the weights. But of course now the main drawbacks of these complex models is that they act pretty much as black boxes. We don't really have much of a clue how exactly they come to a certain conclusion. And this is pretty much what motivated this new research field, which is called Explainable Artificial Intelligence, or XAI in short. And we're going to start with, what is it about? So the Explainable Artificial Intelligence, interpretability, explainability they're very general terms, and everything that we see within the field can pretty much distinguish in two things, in two separate branches. The first one being model transparency. So model transparency is a property of the model itself, and it indicates that we just know how the model works. And so here the setting, we see that we have a transparent model F, and the input X goes in, giving us a prediction, and which then with a ground truth can be used to evaluate through a metric how good the model is, and the user can simply look at results and the model itself and can reason about why the model has come to this decision. It is indeed if you will, like the safest way, the most trustworthy way. However, as you can guess, having a model that is per se transparent means that as of now, F is very, very simple. So we cannot really leverage those complex models, which are pretty much pushing the boundaries of what we can do. And although it's still okay in simple applications where more complex models don't necessarily lead to better performance, as models are getting better, it is declining in popularity. So that's why we will mostly focus on the second branch, which is post-hoc explainability. So post-hoc, to begin with, it just means after the fact. And why that is the case will be clear in a second. So post-hoc explainability is not a model property. It just means that we cannot understand the models alone. So here in the picture on the right, we can see that the model F is now a black box. All the rest remains the same, with the exception that we have something called post-hoc method that we can also call post-hoc explainer, which now can look at the model and can produce what we call explanations. And these convey useful information about the model that we would otherwise not be able to extract on our own. And from here now we can justify the term post-hoc because the method phi is applied after the fact, meaning like after the model F is trained and is deployed, and we can still apply phi. So the development of F has nothing to do with the perspective that it will have to be explained. And that's like one of the probably the biggest descriptor of why they're called post-hoc methods or post-hoc explainability. There are several types of post-hoc explainability that, let's say, pretty much describe exactly what it can be applied to, and also what exactly the explanation corresponds to. And the first distinction that we should make is between local and global explainability or explanations. And in this case, we refer to local explanations. We refer to explanations as local if they are about one specific instance, so one input-output pair, or very few. Whereas like global explanations are more about like the model overall, or at the dataset level, or at the same time could be referring to a large list of instances. And second, we should distinguish between model agnostic and model specific. And this is quite self-explanatory. An explanation technique that is model agnostic can be applied to any model, meaning there's no assumption on what F has to be. Whereas in like model specific can only be applied to a specific model or a class of them. So maybe something that can only be applied to BERT would be model specific, or something that has to be applied to neural networks or to transformers and doesn't really make sense to apply to anything else. That would be model specific. Okay, so now we have this distinction done. So the focus of what we'll do today will mostly be post-hoc methods for NLP. So we're not going to go into transparency, so inherently transparent models. Neither we will go into what was known in the literature as Bertology, which is mostly very deep and specific analysis of transformers, like BERT, which is what gave the name to the subfield. So we will not work on frameworks that specifically try to analyze a model, but rather try to work with frameworks that generate explanations for a multitude of them. And as for the previous lecture, a warning that a lot of the things that we will say here are oversimplified just because of the amount of things that we have to cover in just one lecture. All right, so if you remember from the lecture NLP, the first course, there was a pretty big statement about attention weights that not only give you alignment for free and not only they make performance a lot better, which is very true facts, but that they allow you to interpret the relationship between input and output, which they do to some extent. And therefore the question, but why don't we just look at attention weights as a form of explanation? Because they tell us which tokens the model is currently attending to produce a specific output, be that a word in a sequence or a classification score. And although the intuition is correct, we have to remind ourselves that architectures, since transformers especially, they have a lot of attention heads. And attention heads in parallel tend to learn very different features that serve very different purposes. And it's actually incredibly complex to understand what exactly they learn. And this is perhaps the main reason why researchers highly disagree on whether we can consider attention explanation. And although it probably does work in some cases, for the majority of situations, it doesn't really correlate with the rationale the model actually uses to produce its output. So in short, we need to look for alternatives, which is pretty much what the lecture is about. So I would begin with surrogates. And the idea behind surrogates is that we want to approximate a complex model that for us will always be this black box F model. we want to approximate it with a simpler one, which we call G, that perhaps is transparent. And what we do here is that we have the input going through f, and we get a prediction f of x. And now this f of x can be used as ground truth to train G. And so we have x, the inputs, and f of x as label for training G. And as we give a lot of these pairs to G, G will learn how to mimic f and can give us G of x. And this implies that now G is a very good approximator for f, and therefore we can look at G, which is transparent and is easy to interpret, as a surrogate for f. Now, of course, here our intuition tells us, wait a second, but can actually a transparent model really approximate something that is orders of magnitude more complex? And the answer is no. Otherwise, G would have the same performance as f. And so, like, what would be the point in training f in the first place? If G can achieve the performance of f while being a lot simpler, it means that f is just way too much for the task, and probably, you would have definitely been fine with something much simpler. So the idea here is, okay, G is way too simple for f, but maybe that's the case if we talk about the whole, like the entire model on the entire data set. That perhaps doesn't really apply if we look at the model locally, meaning around a specific instance, so on a very specific part of the decision landscape. So maybe f is not that complicated there. And this is exactly the idea behind local surrogates. And what we have here is that we have the same thing as before. We have our f black box, x goes through, we get our output. But now we don't use the output, like many of these outputs, to train G, because we want G to approximate f around a single instance. So what we do is we have this one single x, which is the instance around which we want to build G, and we generate a lot of fake data around G by perturbing x, and we call all these fake points z of I. And now we run all these z of i's through f to get the output, and now all these outputs that are generated from input-output pairs that are around x is what get fed to G. So the zi's and their output as labels. And now G learns how to mimic f around on these zi's, which means around x. So G is the local surrogates because it approximates f locally, aka around x. Exactly. So now that G is good at doing that, we can simply explain it because G is transparent, to explain the original instance x f of x, because G is a good approximator of f's behavior, at least when we are around x. Okay, so that is how you build a surrogate. Although I haven't really seen it, you don't really see it used that often, is actually surrogates are many times implicitly used in frameworks that are actually very popular, and we'll get to that in a second. But in terms of explanation forms, how explanations look like, the first example I want to make is feature attribution, which are probably the most common type of explanations now with chatbots of this level. We rely a lot also on natural language explanation that we will see later in this lecture, but that is definitely not the case on the broader scale, or maybe to models that are not directly interfacing users. So what's the point of feature attribution? We have an input which is composed of words or tokens or whatever is the level of division of the input, and we want to attribute an importance score to each input feature, aka every word in this case, based on the relevance that they have on the model prediction. And in most cases here we do it at the local level, meaning that if we have f that is a sentiment classifier and we have the input sentence, I like the movie. We want to understand, okay, which word is the most important for F to classify such sentence as, well, I guess in this case, positive sentiment. And of course, it's fairly easy to do. You can already think about basic approaches, which would be, okay, I go one token at a time, I remove or replace a token, I rerun the prediction, I look at how it changes, and then I just take the difference in output with the original. Of course, the more I see it changing, the more means that the token I have replaced was important. An alternative approach, I just take the gradient of the output logits with respect to the input tokens, which is roughly how gradient descent works, but not to the weights, in this case to the input tokens. And as you can guess, the larger the gradient, the bigger the effect that a certain input feature has on the output is. And for those of you who want to look into a very, let's say one of the most straightforward approaches, yet very, very popular and very, very effective, how to combine local surrogates with feature attribution, that would be LIME, which I really recommend to look into if you're interested. And what I will instead look into is a bit more of an advanced version of LIME, which is called SHAP, which has gained a lot of popularity, and it's definitely been the gold standard for feature attribution local explanations for a while. And SHAP is based on a game theory concept, Shapley values, and these are roughly like almost 70, actually exactly 70 years old, and they were initially defined to fairly distribute a reward among a set of players that are contributing to a certain outcome. Now, in the machine learning setting, the reward is an importance score, which is what we want to attribute for feature attribution. The set of players is going to be a set of input features that are playing and are contributing to an outcome, aka for us, the model prediction. And Shapley values are calculated on coalitions. So to get more into the jargon, so we have F, which is the set of all our features, and a subset of it is what we call a coalition. So you can think about it as a subgroup of these features or players that, when are given to the model is going to give a certain output, in this case F of that coalition. And what a Shapley value is, and this is going to sound very complicated, but the next slide will make a lot of sense. Phi F of I, so Shapley value always depends on F, aka the model of I, which is one specific feature, will be the average of the marginal contribution of the features across all possible coalitions. Very complicated, not really though. So I'm going to go to the second part of the slide briefly. So each Shapley value is calculated as such. We have phi of 0, which is like the Shapley value of nothing. It's just like this kind of base value that we start with, is F of X empty, which is just what happens if we don't pass any of the features, input features to F, meaning we just run F with random noise or sort of a default empty input, which depends on, of course, on the task. And then we have phi t, which is the Shapley value corresponding to the input feature t. And this is literally what we said before, is the weighted average across all coalitions. And this is the first sum, which looks very complicated, but just look at the sum. We're summing over all S's in the list of coalitions, in the list of features. So we're summing over all coalitions that do not contain xt, which is the feature we want to attribute the Shapley values to. And then we have a complicated term with factorials, which you can pretty much ignore. It's just needed to normalize the scores. And this is basically, it's useful to divide by how many coalitions you have for a certain cardinality. And the most important part of this formula is the loss, which is literally the marginal contribution, which is the difference between f on an input x when you have a collision with the feature xt, and minus the f on that instance, but without the feature xt. So I have the input x, but we only take input features that are in a collision. And then we add the feature xt, and we take this difference. And this is literally the marginal contribution, aka how much the prediction changes when I insert also the feature xt. And this is exactly how the score for each, basically the feature attribution score is calculated for each input feature. And what SHAP does then implicitly is that the model is approximated an implicit surrogate, which is a linear model whose coefficients are the Shapley values themselves, meaning that we are implicitly building a model g of x that is a linear classifier, which has this base value phi of 0, which is like kind of the base value, like the default behavior of f when you only pass random noise in, plus the sum of all input features, where each input feature is multiplied by its Shapley value, which is the importance of that input feature. And exactly in this way, then this of the implicit surrogate is what actually happens when you use SHAP. But de facto, we're interested mostly in all the phi of t's, which define the importance of each input feature. Now, of course, the problem with this, and I think there was a question in class that was asked exactly on this, is that, well, if I think about the coalitions, there are many of those, because you have exponentially many ways to build S. So this sum is extremely complicated. I mean, it's extremely costly to compute. It means that we cannot do it for all coalitions, so we need to approximate this quantity. And this is exactly SHAP, basically what the SHAP framework does. It's able to compute Shapley values very efficiently. So it has a lot of, it has very solid theoretical foundations, which can be found in the paper, which will be in the references, because of the good properties that Shapley values have, but is also able to compute them as fast as necessary for in the case of machine learning. And SHAP is not specifically one method, but rather a collection of methods that apply to different models and for slightly different use cases. And I'm gonna just mention a couple. For instance, a kernel SHAP is like the model agnostic variant. Then we have tree SHAP that, well, as you can guess, is model specific and very optimized for decision trees and random forests. And then we have deep SHAP, which is optimized for neural networks. And the classic SHAP explanation, local explanation, looks like this, where we have our base value, which is that phi of 0 that we have seen before, which is, oh, if I don't tell anything to my classifier, if I just pass a random noise, it will give me a value of 0.5, which in this case, which is a sentiment analysis prediction, kind of makes sense, right? If I don't say anything, is, yeah, I'm going to say positive or negative sentiment, kind of 50%, which is exactly in the middle, which is no knowledge pretty much. And then the various Shapley values, and I'm going to go back 1 second. So the various phi of t, they get added on top. So they modify phi of 0, which is the base value, to get to, well, g of x, which is the final output, which tends to mimic f of x. So basically Shapley values, when summed up, they make up the difference between the base value 0.5 and the current output, in this case 0.29, which would indicate that if, towards the right means positive sentiment, means that the output is negative sentiment as we came down from the base value. And for each word, we can see the force that they put in a certain direction, like we see negative words. And when I say negative, I don't mean like negative in general, but as they are perceived by this specific model, that they push towards left, whereas like positive words push towards right, and here they're also color coded based on their contribution. Right, so as you have seen, SHAP is very powerful. However, just because of how it's defined, it's not really well suited for text because of the each word. I mean, all words are considered separately. Like we assume that all features are independent, which I'm sure is the case in many applications, like where you have uncorrelated tabular data. But in text, that's pretty much never the case, just because a word is in a sentence, and the meaning depends on the context. So there's no way that features have any level of independency. So the main thing is, well, if BERT and stuff, if they use context, well, so should explainers, which is the intuition of Hedge, which builds hierarchical explanations that can attribute relevance to also multi-token features. So not only to words taken singularly, but also to combinations of them. And you can pretty much imagine it as, starting from the entire sentence, and as we go down the hierarchy, the sentence gets broken up in, subtokens, and basically Shapley values are calculated for each layer. So in this case, there's one Shapley value for the entire sentences, and then for the various sentence components, and it keeps getting broken down until you reach the word level. The way it's broken down, it's based on weakest token interaction. However, that's not super important. You can use whatever idea you want to break the tokens apart, as long as you keep applying SHAP or a feature attribution method at each hierarchical level. That's the important part. So this way you get a more holistic perspective on feature importance at multiple granularity levels. This, of course, doesn't really apply to very long inputs, because otherwise the explanation would be massive. But for instance, for sentiment analysis, when usually sentences are not that long, that works actually very well. Okay, so that kind of concludes the chapter for feature attribution. Now we look at another type of explanation, which is influential samples. Now in this case, we don't want to attribute an importance to input tokens or input features, but rather we want to, so given a certain input, so one single instance. So again, we're talking local in that case. We want to select samples from the dataset that are actually very similar to the current input. Now, the notion of similarity, of course, is not like in general, but rather according to the model. So we want to find input samples that are processed similarly and therefore influence each other during training. And the way you do this is influence functions, which here on the left we see we're interested in modeling the difference between the loss on a specific instance. So for instance, we say loss on the couple yx, which is just a single instance input-output and parameters theta. And we want to say, okay, what's the difference between that and theta tilde, which is just the loss if I didn't have a certain instance x tilde in my dataset. So in this case, I'm trying to evaluate how much x tilde would influence the training for x, which in a way basically tells you very much the similarity from the perspective of the model between x and x tilde. Now here on the right, there's a quick approximation how to calculate that. Otherwise, this would be very, very complex too. You would have to retrain the entire model and then basically run the two predictions. This can be approximated quickly. However, the formula on the right is not too important to remember. Now, of course, you don't do that. That would be very, very complex to do every single time. What is actually a bit more practical to do is to accumulate loss changes during training. So let's say you pick a test instance X, which is okay, I want to I have some of these test instances, and for each of them I want to kind of keep track of what are the most influential samples for it. So I just take X and then I look at the loss on X changing as I optimize, as I'm training my model. And I look at the loss changes specifically when I am optimizing for X tilde. And you just keep this for many samples. And ideally you would consider every single update, like, okay, anytime that I'm approximating for X tilde, which might happen at many steps, I just look at how the parameters change and how that change in parameters actually changes the loss. So ideally you should do this every single time you're updating the parameters because of X tilde or because of a sample belonging to this test instances. However, in practice this would be incredibly tedious to do. So you just, what you do, you just keep, whenever you're training the model, you just keep track of batches and model checkpoints. So basically keeping a lot of that metadata allows you to basically after the fact to retrace and look, oh, basically when we had that specific batch, we saw the model getting a lot better on this specific instance, meaning that in that batch, there have to be instances that are similar, and then you just perform maybe a more in-depth analysis only for that specific batch. Yes. So that was the second type of explainability, and now we're going to go into the third type, which are arguably one of my favorites, which are adversarial examples. So adversarial examples are inputs that purposely fool a target model into making a wrong prediction. So they're mostly known for classification, as actually as most explanations are. They're mostly focused for classification, especially in NLP. And adversarial attacks, maybe they don't convey a lot about the reasoning behind the model, although they're incredibly useful to discover weaknesses of the model that you're trying to deploy. And they do expose when the model is relying a bit too much on specific input features. And of course, usually trying to fool your model and then understanding what are the vulnerabilities that it has. It's the first step to actually having then good defenses or fix certain bugs and that then lead to a higher robustness. And before we get into the details, there is probably one rule of thumb so far that you can learn from working in adversarial examples, which is if you want to find good attacks, you just have to try a lot. So a lot of the methods that you will see maybe in your career that deal with adversarial examples, they're just very greedy. Like they have to try a lot of combinations until they manage to crack the model. Yes. So in NLP, we have a variety of attacks depending where they try to apply the perturbation to fool the model. So here we have an original sentence, which is again for sentiment analysis. And we have, okay, this is a great movie. Too bad it's not available on home video, which is classified by the model as positive sentiment. Makes sense. And then we have a word level adversarial attack, meaning that the word level refers to where the perturbation takes place. So here we have, this is a solid movie. Too bad it is not available on home video. And whereas for a human, this would be okay, weird word choice, but legit, still positive. Where somehow it exploits some statistical correlation that was learned by the model, and now the model says negative. So it was actually successful at fooling the model. And in the same way, we can see a character level attack where grade has a second instance of T, which again, out of vocabulary word, fools the model again. And then we have sentence level adversarial attacks. In this case, what a splendid movie I see. I wish I could bring it home with me. And what you see from sentence level attacks is that they're often weird, like they don't sound natural at all. And the reason is a lot of the methodology that is behind sentence level attacks, it's usually works with style transfer, meaning they don't recreate the sentence just to sound slightly different, but rather they have to use the style from maybe Shakespeare to try and convey meaning that is similar, but that somehow fools the model just because it uses weird words. And so there haven't been too successful so far. Definitely not as the level of word level adversarial attacks, but I think it's just a matter of time.
So, as we said, of course, what operates at the character level, it's way more based on visual similarity. But what you have to understand is that the visual similarity is something that only we as human perceive. Like, for us, E and E with an accent, like for us, they're similar to C, but for the model, just like a character, like they're two complete different characters. They're not more similar than an E and a D, or an E and an F. So what you can do here is that I can just start replacing letters, and I can say whatever word I want. Like I can say bad words, just replacing character by character. And whereas we can still read because, well, we know the visual of it. For the model, it's just like exclamation mark D10T. Like that's embedding-wise absolutely nothing. And this is actually a very, very effective way to simply confuse a model. The problem is, the good thing is that, well, if I use a spell checker, I find out those attacks very quickly. Because of course, one of the reasons why we also study adversarial examples is not because we like to fool models, although that's also part of it, but we would like to understand how to defend ourselves when we're attacked. And spell checkers, when we have things that operate at the visual level, they're usually a good defense across, let's say, most of the standard things. Things get a bit more complicated at the word level, because of course now we want to introduce something that fools the model, but yeah, we're not really allowed to go out of vocabulary really. Like we can change a word, but the meaning has to be preserved, and we can't make something that is just great with two T's. The nice thing here is that word level attacks, when successful, they're way harder to notice because it's just a synonym. And although the sentence we've seen before with solid, yeah, it does sound a bit weird, but I mean, if you see it, you wouldn't, without knowing that it's an adversarial attack, you wouldn't really think about it too much. And one example of method here is PWWS, where very simply you just take a sentence that you want to use as an attack, so original sentence, and you start changing words until you fool the model. And that seems like an extreme greedy strategy, but for enough tries, it will work. What PWWS uses further to reduce the space that it has to search for this adversarial attack is by looking at what features, like what input words, are the most profitable to perturb. And how do you do that? What, sorry? For instance, like if I know the highest SHAP score for a given sentence, I know which tokens my model is mostly relying on to produce this output. So if I go and attack those first, it's way more likely that I'm going to change the behavior or the classification output of my model very quickly. And that's usually how it's done. Okay. Then not the last type, but definitely the one where I have the least to say is natural language rationales, where very simply you want the model to give you prediction and explanation in the form of natural language. Why is this important? Because, well, we've looked at feature attribution, we've looked at adversarial examples, and sure, we probably work in the NLP sector, we kind of understand what it means, but if we take a random person, I mean, it's like, okay, I don't know what that is. And that's why we want to, that there's research into generating human understandable explanations. The problem is, these are often just like made up by the model in a way that they're plausible, but they don't necessarily need to reflect what the model is actually doing. And the way this was done before, and before, I mean before instruction following models of a decent size, is you had to train on a data set that for each input-output pair would also have an explanation triplet. meaning I would train a part of the model, in this case, to generate the label, meaning the classification label or whatever the task is. And then I would need to have additional layers on top that from the same latent state try and generate the explanation learned from this data set. Incredibly limited. Also because then we fall back in all the problems that machine translation has, summarization has, and you'll see that in the second block of having this golden label that you need to follow. You don't really have room for creativity. So this was the way it was done before. Now, well, that's a lot simpler. You just go to ChatGPT and tell me, and you ask, why have you prompt this? And it tells you why. The problem is what it tells you is just a linguistically and natural language probable way of answering your question. It can be completely uncorrelated with what it's actually doing. Even, I think we had a discussion with someone about chain of thoughts the other day, and there was a question asking, but when ChatGPT tells me that 5 plus 2 is 7, is it truly understand what 7 is? Or is just like, what is it instead? And the answer is very likely not. I mean, we don't know exactly what's the level of understanding, but at least from a statistical perspective, it's very likely that on the internet, you just have many times 5 plus 2 equals 7. And by seeing that over and over, you can incorporate that in the billions of weights that you have available, and then reproduce that when needed. Exactly. So on a very practical level, the way you enforce this, you can do it either by explicitly requesting the model to produce an explanation, or by providing answers that reflect the type of explanation that you want, and that's chain of thought. So I provide a prompt, and I also give the answer. So that would be my demonstration, as we saw in the fine-tuning lecture. And then I ask the question that I'm actually interested in. And if my answer in the demonstration is formulated in a way that has really step-by-step solutions to the question that I've posed, then likely the model will pick up on that and will keep producing answers that follow the step-to-step type. Yes. Finally, probably the most complex type of explanation are concepts. And here is going to be very fluffy, because concepts, there's no way, at least for now, there's no agreement of what exactly a concept is. So we can say it's an intrinsic property of or learn feature of a model we want to test for. Now, the problem is these concepts can be at various granularity. For instance, in computer vision, maybe it's a bit easier to explain, is that if I have a model that classifies a picture of animals, well, in this case, we go from a picture of a zebra to a zebra, then one possible concept could be stripes. So something that is somewhere between a zebra and the concept of it. So if you go from zebra to zebra, it's probably some neuron or some groups of neuron in that computer vision network that recognize the pattern and are then able to, well, help the classification. And of course, concepts can be at all sorts of levels. There are concepts that are identified by certain layers, and we know from computer vision that the level of abstraction of concepts keeps increasing as we keep going through the layers from the input direction output. And so there are entire layers, but also single groups of neurons or even single neurons can actually learn specific concepts. And one example of it is, I don't know if some of you is coming from a bit more from the computer vision domain. If you know how deep dream works, you just take one neuron, and by amplifying the activation of that neuron and optimizing for the input, I can find the input that basically makes this neuron fire the most. And if I find the neuron that recognizes dogs, then I can make images with dogs everywhere. And that's how deep dream works. In NLP, you can kind of do the same. However, concepts in the NLP field are more, they're usually words or just like small sentences. They either reflect something like gender, ethnicity, religion, parts of speech, so linguistic stuff, semantic concepts like space and time, lexical concepts, or even maybe what I call non-linguistic concepts, so maybe things that we put in text but do not have a semantical meaning per se most of the time, like brackets, emoticons, and so on. So for instance, in the classical sentiment analysis task that we've been looking so far, concepts could be, well, adjectives that are either positive, neutral, or negative. And we could test for those, meaning we're interested in finding those concepts that the model has learned in order to function the way it functions. Meaning, okay, what are the most important concepts that my model is relying on to perform this task? And one way to test for those concepts is to use something like TCAV, which, given a set of concepts, it will tell you, yes, it gives you a quantification of how much the model relies on them to function. The problem is methods like TCAV imply that I need to come up with the concepts, and as a human, I'm very biased. However, they usually are the best in terms of working with concepts that are human understandable because we define them, and usually they're very accurate in the measures that they give. On the other hand, there are actually more complex models like concept SHAP, which, as if you guessed from the name, is a concept level explanation, but that still relies on the same idea of SHAP. They can extract concepts in an unsupervised manner, meaning I do not need to define the concepts that I want to test against, but it extracts it automatically. Although, as you can guess, when you try to extract stuff automatically from these huge networks, it does happen to be often like nonsense, or just like words that happen a lot but do not have a lot of meaning. And then you need to do the interpretation after of this. Yes? Yeah. And the output is a list of concepts. And those can be, I can make an example. So let's say I say concept SHAP, but we'll see an example of this later as well. Let's say concept SHAP, this is my neural network. I want to know what are, you have to still give the number of concepts. For instance, I want 4 concepts, and for each concept, it's going to give you the words that most represent those concepts, and also the usually a few samples that really fall in that category. Yes, that's pretty much what they do. And ideally, if you look at the set of concepts that you have extracted, they should give you a signature of the entire model behavior, ideally. It doesn't really happen that often. Yes, there's a question behind you first. I think you need to speak up a bit. I can't really hear. So these tools, I consider them like my research of interest, but they're slowly becoming mandatory just by default of legislation. Now, I'm presenting more than tools, I'm presenting types of tools because I want to give you the idea of what's out there and what to look for. It really depends on what the goals are. So if I keep jumping to other fields like computer vision, but if I want to find a tumor on a tissue from an image, probably I'm interested in looking at things that are similar. So maybe I know how a similar image was classified, and I want to find those images that are most similar so I can compare. Or maybe I want to look at feature attribution, because then I really look at what the model is focusing on when it's making a certain diagnosis. Personal opinion, I believe that seeing how NLP is going, influential samples will play an increasingly important role because texts are getting longer. Feature attribution, it's hard to apply when text gets so long, and therefore you have scores that need to be distributed across a very large set of tokens. At the same time, most of the tasks are also getting more complex. Like, we're moving away from this classification setting to summarize, do all possible things, and knowing how exactly each token played a role, it's decreasing in importance. However, I think it's important to understand what tokens, or more than anything, what samples or what documents have you seen at pre-training in order to give me this answer. And we're slowly moving towards that direction. And therefore, I feel like knowing what samples, or like what's the fundamental knowledge that you have acquired to answer this question this way, will be increasing in importance. What, sorry? I don't hear, sorry. Yeah. You're deconstructing the way, like, you're asking, what have you seen at training time, so that now you see this and you tell me that. So I feel like it's influential samples, it's trying to build the bridge between what you see at inference time and what you see at training time. And although the methods are still fairly simple, it seems like the type of explanation that it's likely to seem very appealing at when we use these language models. Of course, now we're talking from a machine NLP practitioner perspective, right? The public will just care about natural language explanation in most of the cases, I assume. Okay. We're going to do take it later. We're going to do a very simple example about TCAV. So how do I compute the importance of a given set of concepts? And let's assume that I have picked these adjectives as concepts I want to test against. And I want to understand how important they are for my model. Specifically, as I said, you don't really test for the model as a whole usually, but you test for a part of it. In this case, I'm interested in this layer. So we have the layer that I've called L. So we know that there is a transformation that goes from the input up to the layer L. And then from the layer L, we're going to go to the final output, which in this case, we can just assume it's just one score, positive, negative, neutral. What I do, I just apply f of L, meaning model f up to the layer L to these adjectives, which, well, can be just passed as input. As you can guess, this will give me a latent representation because I do not compute until the end. So this will be vectors of the size m, which is just like the size of L, the layer L. And then I just take a linear classifier on them. So I just compute what's the linear classifier that would separate them in their representations. And I take the orthogonal vector to that, well, hyperplane. And now this vector, which we call concept activation vector, is basically the vector that defines the direction for belonging to a certain class. So if you think about the hyperplane that says, well, approximately everything below will be belonging to this class, everything above will be belonging to the other class, the vector that points in that direction, that's pretty much what defines being of that class, like as a direction. So we have that vector. So what we can do, we can compute the attributions for a given test sample within respect to the neurons in layer L, which sounds a very complex way to say we compute the partial derivatives from the output to the neurons of that layer L. And as we have seen, that's a possible way to contribute important scores for that specific layer. So basically, you're asking for these specific inputs, how important is every neuron in this layer? And you compute that. Then you say, okay, I have the importance of each of my neurons for a specific input, and I also have the the concept attribution vector. If I do a dot product between them, I will get their similarity. So very, very similar concept to attention here. I just see, okay, how are these related? And by computing that dot product, I see how the sample is connected to the concepts that I have chosen. At that point, this will give me a score, which either indicates that it's either going to be positive or negative. Usually it's positive if the sample is very connected to the concept that I have chosen as positive. In my case, one of the label is positive. And then I have all the other ones that are going to be negative. And then I can just count for how many samples do I have that have a positive scores divided by how many samples do I have full stop. And this is going to be a ratio, and it's the ratio of samples that are very connected to the concepts. This is like what it measures exactly. And now you're asking me, you could ask, why do I care about measuring the numbers of samples that correlate with my concepts versus all the possible samples? Well, the reason is because you want to understand how those concepts mostly represent the samples that you have in your dataset. And the point here is, if I start to pick all samples that belong to a certain group, for instance, a class, that's like the simplest and also most useful way to do it, I can look whether these concepts are a very good summary for a class in general. So ideally, if I get a score of 1, it means that all the samples that I have chosen have a positive score with these concepts. And if I've chosen all the samples from a class, means that all the samples from this class have a good interaction with this concept vectors, meaning that concept vectors are a really good summary for that class. Sounds very complicated. It will not, believe me. So now I've done an example specifically for the positive class of a sentiment analysis task. More in general, what you do, you measure how many samples in a class have a positive dot product with the concept I've chosen, divided by the number of samples. That's it. Very simple. And you're like, okay, I get a score, and is 0.7 good? Is 0.9 good? There's not really like a precise threshold. The point is you want to pick several sets of concepts and then measure the score for each set that you've picked. And although there's no specific number that tells me these are good concepts, you can definitely compare scores. Meaning that you want to go and pick the set of concepts that give you the highest activation score. And that's how you pick the concepts for a specific model. Of course, what's the issue here? The issue is that, well, you've picked the concepts, meaning that you've picked concepts that sound reasonable to you for the task that you're working with. There's definitely a bit of human bias. And of course, so therefore the score itself doesn't really carry a lot of meaning in terms of exactly what the model thinks, just because you came up with these terms. And solution to that is testing with as many sets of concepts as possible mitigates the problem, because you're making the base larger for what you're testing against, meaning that you're more likely to find a set of concepts that actually describes the group of samples that you want to describe. Right, this was the supervised method. Unsupervised. We're not going to go into how it works, because this one is really complex. But the whole point here is I would like for you to understand at least how an output looks like. So this actually comes from a paper in which they've looked at student surveys where students in American colleges, they had to fill out, okay, these are questions about my background, about my interests, about what I want to do and stuff, and they were trying to predict what the students would actually do after college. And once trained a BERT model that would take all the all the answers from the students and then predict what they would do, they said, oh wow, probably this model has figured out a lot of stuff, and we could either look at the data or we could look at what the model has learned and try to learn from the model instead of from the data, because it's just a lot faster. And so they ran concept SHAP to extract 4 concepts from the model. And there were, in this case, well, there have to be 4 answers. And for instance here, for the concept 1, there were sentences like, oh, I want to be successful, find a job, my own business, no thanks. So you see, like, you have sentences or like subsets of sentences that appear in the data set and most relate to a certain concept that was found. And when I say the most relate to a concept, they're actually the closest in the embedding space. Because at the end of the day, the concepts that you find are words or, well, groups of words, meaning that they have an embedding, meaning that they're actual vectors in your embedding space. And so you can find the nearest neighbors, so sentences that describe these concepts. And you can also look at the word cloud, which is usually the words that tend to appear the most in the sentences that are close to these concepts. Yes. That was it. Mm-hmm. So I'm not sure if I... Yeah. So it wouldn't really work that they're... Like, it's good to do it in a hierarchical way because you don't know a priori how many concepts you want to test for. Usually you just go in ranges. Like, either you test from 2 to 10, or maybe you test from 20 to 50, depending on to what granularity you want to get. But definitely testing for a range of them is a good idea. Point one. Point two, so I feel like there's probably a different thing that you want to get out of the explanation. So now you mention how a neuron contains or represents or identifies a certain concept. To do that, you basically, so whenever you run a concept explanation, you always run it for a part of the model. So of course, you go, so the example that we did was for a specific layer. I could have run it just for a specific neuron, which is a bit nonsensical because then I only have one derivative, but it still works. So when you compute concepts, you ask, what are words or what are conceptual things at the embedding level, because we're in NLP, that most represent what this part has learned, or what most represent usually also for a certain class. So any concept refers to a part of the model for a class. And then you would have to, of course, repeat it for the parts that you're interested in and the classes that you're interested in. The other thing that you mention is like, how important is this neuron? Right? Which is a different question, and it's not quite on the concept one. And we have seen today how you can actually calculate that. Not exactly that, but almost the same. Can anyone guess? There's one type of explanation that we've used to measure something, but that same logic could be applied to, well, anything in the model. Yeah, feature attribution. For instance, if I can look at the contribution of specific coalitions at the input level, nothing forbids me from doing it from neurons like somewhere in the middle of the network. Even if we take simpler methods, like just computing the derivative, the partial derivative from the output to the input, I don't need to go all the way back. I can just stop, somewhere in the middle, and that's going to be the relevance that each neuron has for that specific output. It works exactly the same way. Feature attribution are per se a very special case of contributing importance of model parts. Specifically, we're picking the input. Another method that wants to calculate the importance of each neuron for the output is, well, gradient descent. We just compute how important that neuron is, and then we change it to fit better our loss. It's still the same logic. Exactly. So here, what were extracted were 4 concepts about students' plans, and the 4 that came out from the analysis were, the first one was the lack of a precise plan, personal determination, the type of plan, and also the plan timeline. Because here is all about, well, what the plan was in the students that filled out the survey. What I'm trying to convey here by showing this very complex example is that, yes, we get the job done for us, which is great. We don't need to come up with concepts. We don't need to inject our bias in the selection of concepts. But concepts are not going to look that nice. They're going to look something like the statistically more relevant thing for the model when dealing with these type of samples. But it's not going to be like a nice adjective. It's really rare. Yes, so that was pretty much it for the concept explanations. Okay, there's one extra slide. So the first thing I want to say, and I think there was also one question at the beginning, like, oh, but local explanations look only at a specific instance. What about global ones? Well, one way to create a global one is, of course, to put together a lot of local ones. And so, for instance, if you aggregate them, if you aggregate feature attribution explanations as we know them at the local level, which SHAP is, you can get a global one. And a global feature attribution explanation would just mean how relevant that feature is for the model as a whole, which is really hard to estimate because what does it mean for the model as a whole? I mean, for a specific instance, usually it's like, is it more positive? Is it more negative? For the model as a whole, we have all classes put together. Usually it refers to model performance. So what are the features that the model relies more to learn in either directions? So either as one class or the other. And so one way to compute global feature attribution explanation is to I select B input feature. So B is a number, which is my budget in terms of what I can compute. And then I compute local explanations for all of them. And then I will take the, for instance, the absolute importance of each feature that appears in the samples that I've computed the explanation for. And by aggregating, for instance, summing up, that will be the importance of that specific feature overall. Not a super popular method because obviously it's very demanding in terms of computations. Then, that was it for, let's say, the type of explanations that you can encounter, or probably that you might look for when you want to explain something. But there's, of course, a crucial point that I would like to talk, which is the difference between what you could possibly be evaluating. So we've already mentioned it when we came to the point of natural language explanations, but this is pretty much everywhere. So whenever I get an explanation from the model, there's unfortunately nothing obvious that's going to tell me this is good or not. This is just an explanation. We don't have metrics like we have for models. It's not that well defined. So there are usually two ways that we use, and first one is plausibility, which I'm afraid is the most common way to go about it. So you look at it and you say, ah, this looks reasonable, or this doesn't look reasonable. But the thing is, you're evaluating from a human perspective, which is really not the way to go about it. So plausibility, as I said, you look at whether explanation look convincing or align with human rationale. Which is good if you want to build something that explains like human rationale. If that's your goal, if your goal is to achieve plausibility of explanation, that's how you do it. But if you actually care about faithfulness, which measures whether the explanation truly reflects what the model is doing, then of course plausibility is just not the way to go. And here I would like to bring two examples that show you that these two things do not have to correlate, like 0%. So let's take ChatGPT, for instance. So we have an incredibly accurate model in most tasks, which can probably generate the most plausible explanations I have seen so far. I mean, when you ask it why, it looks good. Let's be fair. So plausibility, extremely high. Faithfulness, absolutely 0. There's no way to know if this thing is actually faithful or not. Let's take a second thing. Let's take what I've put here is a single head attention classifier with few layers. So we can even, okay, maybe LSTM is already a bit too complex, but let's just consider a few layers that have a single head attention scheme somewhere in the middle. Now, this is a very simple classifier, meaning that you put the input in, get the output out, you look at the attention, scores, and since there's only one head, well, those will give you exactly the measure by which each token in the output attends to the two tokens in the input. As faithful as you can be. Like, wow, I mean, it gives me exactly that measure. But when I look at it from a plausibility perspective, I'm like, cool. Like, this doesn't really mean anything, or I don't believe that this word should look at that one. Because that's my perspective, because that's what we do as humans. But the point is, the model will just do what's statistically convenient to do. And the thing here is, you have an explanation which is extremely faithful, because I want to measure the alignment, for instance, between input and output, but it could look nonsensical to me. So the second example is something that can be very, very faithful, yet not plausible at all. And of course, that's what you're actually measuring. So we have these two things, faithfulness and plausibility. Unfortunately, usefulness as a metric depends on who you are. So probably if you work in machine learning, for you an explanation that is useful for debugging is something that is faithful. For someone who's just chatting with ChatGPT, is something that is plausible. So even the criterion of utility very much differs on what you want to get out of it. There are usually three very broad categories in which we try to evaluate explanations. The first one is we take the model, we put it in the task that it's supposed to perform, maybe even as support for something, and then we ask real humans that work in that real application to do, well, an accurate evaluation of it. So for instance, if there is a psychologist that uses a model to detect when there is depression or anxiety, from online posts, then they look at the explanation of the model, they can very much judge whether that explanation is correct from their perspective. Human grounded, exactly the same thing, but for simplified tasks. So we don't need experts anymore. Now we can just, for instance, look at a sentiment analysis task with movie ratings. And well, any one of us, I guess, can tell whether an explanation from the model looks plausible on why a movie is good or not. Finally, functionally grounded, possibly also the hardest one to explain. You don't have any human for evaluation, and you sort of use proxy tasks. So for instance, if I look at feature attribution explanations, what I could do is, okay, I don't want to use human in the evaluation, so I take my data set, and I know that certain features are that important for a specific input, or perhaps for the model as a whole. So what I do, I actually remove them entirely from the data set, and then I rerun my experiments that I was running. Very costly, although probably less costly than hiring doctors to evaluate MRI scans explainability. And then you measure that. So of course, these approaches vary a lot in terms of what they measure. So it's not always the case, but in most cases, things that involve humans are they tend to evaluating plausibility, because we always measure, this is the explanation, this is what I think a good explanation is, how do they differ? Whereas like functionally grounded methods, they tend to evaluate more faithfulness. The problem is it's really hard to come up with a proxy that actually measures whether that's what the model wants to do. Right, so these are the settings. Finally, since I thought I think it's kind of hard to convey what a functionally grounded method for evaluation is, I just thought I would bring one example. So let's imagine we have a feature attribution explanation. So once again, we have input, output, model, and then the explanation will tell you which parts of the inputs are relevant for that output. This is what we've seen pretty much in the middle of the lecture. And let's assume we have a document classifier. So we fit the documents in, and the model F that we know nothing about tells me oh, this is green, yellow, red, whatever those classes are. And then what we can do, we can take a bunch of those documents together and we just like concatenate them. So now I get a document that is hybrid, that I have parts that belong to class red, that I have parts that belong to class yellow, and so on. And then I just feed it into the model, and the model is going to give me an output. In this case, yellow, but actually it doesn't really matter what it gives you, because then you can take that class, and I can say, and I can ask the explanation method, please tell me which parts of the input are the most relevant for that prediction. And if the class that I'm considering is yellow, then the explanation method should point to the yellow parts, or to the parts that belong to the yellow document. So, although of course you definitely have some variance, this is something that you can scale very easily. And if you can scale very easily something, then you can functionally grounded, you can measure in a functionally grounded way whether this explanation method is able to recognize which are the parts that are most relevant for the model to actually classify this as, well, we picked yellow. So this is an example of functionally grounded method. I brought one because I thought otherwise it's kind of hard to imagine one. Good. So when it comes to choosing a setting, there are kind of rule of thumbs that I tried to put out there, but of course, as I said, most things that involve humans, they're skewed towards plausibility. Most things that do not, hopefully, will tend more towards faithfulness, which I believe should be the primary goal of evaluating explanations. But plausibility is actually the easier to evaluate just because any one of us can do it. And needless to say, having a model or an explanation method that has more plausible explanations rather than faithful, it's usually also what becomes popular. Because in the end, we choose what model is best by the way it feels. And that's also why ChatGPT is famous, because it feels correct. Like it feels right and it feels accurate, though there's no faithfulness behind those explanations. And of course, beyond the discussion of faithfulness and plausibility, there's also the aspect of costs. It costs to hire professionals to evaluate a certain explanations. It doesn't cost to, or at least not as much, to scale things on a functional way. So to design experiments like the one of the hybrid documents that can measure this automatically. Right, last but not least, I guess many of you probably have not worked with explainability. So maybe a few libraries that are useful. And there's for sure more, and there are more that come out by the day. One that we have used with some students, definitely SHAP, the official library, though I have to say it's been, I don't know, like lately they haven't really maintained it as well. Or another one that works very well for PyTorch is CapTum, captum.ai, if you want to Google it, which is built for pretty much any PyTorch model. And when I say PyTorch model, that includes Hugging Face. And when you include Hugging Face, you're pretty much including 99% of the models out there. Also, it can check for multi-model inputs. Probably here I wanted to write multimodal. And has a well-maintained library and documentation. You have pretty much almost everything we've talked about today and more. And for those of you who will actually go and check out the library, you will see that you have feature attribution, and then you will have layer feature attribution and neuron feature attribution, which is exactly what we were talking about before, is applying the idea of feature attribution not to a specific, not like from output to input, but rather from output to wherever in the middle you care, or even the other way around, from wherever in the middle you care to the input, meaning which tokens in the input fire the most a specific layer or neuron. Yeah, so these are some references that might be useful for some of you. As always, references if you want to dig more. And for today, study approach, minimal, that works for the exam. Just work with the slides. Otherwise, reference 1 and 2 are pretty useful. It's more about general interpretability and interpretability for NLP. And if you really want to go in depth, then look also quickly at 3 and 4, which are 2 tutorials from conferences from last year. And otherwise, there are 4 papers, 7 to 10, that go way more into details. And if you really care about that specific part of explainability, then they can definitely be interesting, including, for instance, the hybrid document paper. All right. That was it. And that was also it for the lecture of this block. So, quick summary. We've looked at large language models, what they are, what they were, what are the principles that guide their development, why possibly they work. I mean, a lot of things in this block are, I think it's this way, I hope it's that way, we assume, it looks like. There are not a lot of clear answers because they're so new, and I am also learning as I go through this lecture, almost as much as you are. And that was lecture number 1. Then lecture number 2, we were like, okay, that's all the stuff that happened, cool, how do we actually use them? And we were about fine-tuning what are the most efficient ways to use the large language models when I don't have the resources, or when I have not as many resources as maybe some companies have. And then how do I train something smaller? How do I train something for a specific task? Basically anything that would get from a large language model to something usable for specific applications. Third lecture today is what methods are out there for explanations. If I want to explain what parts of the input are important, what samples are mostly correlated with the one I'm looking at, what concepts are behind the knowledge that the model has accumulated, and stuff like that. So yes, this was the idea of the first block. I will see you next Thursday. We'll have the tutorial. You have gone through the notebook already. You see there's just a few coding assignments. It's mostly about getting used to Hugging Face and like the functions that it contains and how to, let's say, a bit of an introduction to it. And then you have other questions that are, well, they're practical, but there's nothing to code. And it's more about, oh, you have to build this type of pipeline. How would you do it? Why would you do it this way? And then I insert a constraint, and that constraint means something. Or maybe what model would you not use to do this and why? And also, oh, I want to generate explanations about this model, and I would like them to look this way. What do you look for? Or maybe another way. You are using this method to get an explanation out of your model. How do you expect the output to look like? Stuff like that. Okay, that concludes. If anyone has questions, feel free to come in front, and I'm happy to stay here as long as necessary and discuss.